Let R be the region in the first quadrant bounded by the curve y and the line y is equal to secant inverse of x and y is equal to pi over 4. Suppose a tank that is full of water has the shape of a solid of revolution obtained by revolving region R about the y-axis. How much work is required to pump all the water to the top of the tank? Assume x and y are in meters. The formula to find the work required to lift the water in a tank where it goes from A to B corresponds to the vertical extent of the fluid. A of y is the cross-sectional area of each horizontal slice, and d of y is the distance the slices must be lifted. So we have this equation here that we're going to use. Okay, so we have this equation, and we also are given these functions up here. Okay, so the first thing that we want to do is graph this thing. Okay, so what this is going to look like if we graph the two things, y is equal to inverse secant of x and y is equal to pi over 4. Now this is going to be in the first quadrant only, so if you're graphing this in a calculator, you would need to zoom in pretty close to 1, 1 in the first quadrant. Okay, so I'm only going to give you the first quadrant look at this. And the secant function, if you zoom way in where these two connect, is going to look something like this. And then you've got the pi over 4 function that looks like this. Okay, so the area that's going to get rotated around the y-axis is this right here. Okay, and we know that if it's being rotated around the y-axis like this, okay, then it's going to create a circle. And we also know that we need to solve this thing for x to get it in terms of y. Okay, so if I take that function y is equal to inverse secant of x, and I apply secant to both sides, basically I would get secant y is equal to x. Okay, and since I know that this thing is being rotated around the y-axis, it's going to create a circle. I'm going to use A, the area right there, is equal to pi r squared, where r is the radius, which is the distance that this function is away from the y-axis. Okay, so that's going to be your circle. So the distance is obviously going to be this inverse secant function, or actually it is a secant function now that we've solved it for y, so secant y. Okay, so using that, I can say that a of y, function that we're looking at here and in this formula here, is going to be equal to pi r squared, where r is secant. Okay, so we replace the r with a secant, and we get pi times secant squared y. Okay, so that's the a of y that goes in here. Okay, and now we need to figure out what the d of y that goes in here is. Okay, so the d of y is going to be the distance that this thing, that the water has to travel to get out the top of the tank. Okay, so that distance is the difference between here. Okay, the distance between pi over 4, which is this line, and the secant, which is this curve. Okay, so to do that, we're going to say, well, it needs to travel a distance of pi over 4 minus y. Okay, so pi over 4 minus y is how far. And what is the y? It's going to be just some arbitrary y value depending on where the water's at. This is pi over 4 minus whatever that y is. So d of y is going to be pi over 4 minus y. Okay, and we're already given that this Greek letter rho is equal to 1,000 kilograms per meters cubed, and of course gravity is 9.8 meters per second squared. Okay, now we're going to leave this in terms of p and g just so that the numbers don't get really big. We'll plug them in at the end. Okay, so let's go ahead and write down our integral using that formula. So we get w equals the integral from 0 to pi over 4 of rho times g, and then we know what our a of y is. It's pi secant squared y, so times pi secant squared y, and then we know what our d of y is. It's pi over 4 minus y. That's all with respect to y. Okay, and we're going from 0 to pi over 4 because that's our limits um, based on this. Okay. All right. So how do we want to go about solving this? Well, we need to split up these integrals. Okay. So let's put the rho times g out front. We can bring the pi out there out front as well. Okay. So we get w equals pi or rho times g times pi from 0 to power of 4. And then we'll distribute this secant squared y to both of these terms inside. So we get secant squared y times power of 4. And then minus, and I probably should have put the power of 4 at the beginning. I'll take care of that in the next step. And then minus y times secant squared y. Y times secant squared y. And that's all with respect to y. Okay. So this is going to be, we're going to need to split this up into two separate integrals. Okay, so we'll say we'll split it up into this. Our first integral will be from 0 to power of 4 of this, so pi over 4 times secant squared y dy. Okay, and our second integral will be this one, so minus this 0 to power of 4 of y secant squared y dy. Okay, and I'm going to call this, I'm going to split this up into two separate problems. I'm going to call this one here, we can keep that out front, integral 1. And all this I'm going to call integral 2. And I'm going to do this in two separate spots. Okay, so let's first start with integral 1. That is going to be the easier one. Okay, so I'm going to leave the rho and the g. I'm going to figure out what these integrals answers are, and then I'll bring them back. So I shouldn't have underlined that. I'm going to leave these three things alone and just focus on this integral here, and then I'll come back and put them in. All right, so integral 1 will be the integral from 0 to power of 4 of secant, power of 4 times secant squared y dy. Now, the integral of secant squared y is tangent. Okay, so this becomes pi over 4 tangent of y, and then we're going to integrate that from 0 to power of 4. Okay, so that will give me, let's see, equals to power of 4 times tangent power of 4 minus tangent 0. Okay, tangent of 0 is equal to 0. So this becomes pi over 4 times tangent power of 4. That other term cancels. And quickly, let me swing back to the reason that we were able to leave this rho and g and pi alone. Those are all considered constants. They're just numbers, so nothing's going to happen to those numbers. They're just going to stay the same numbers they are, so we can sort of ignore them and then put them back later. And we'll take care of that in a minute. All right, let's take a look at integral number 2. Okay, integral number 2 is the integral from 0 to power of 4 of y secant squared y dy. Okay, so how we're going to tackle this one is going to be integration by parts. Okay, integration by parts says that if you have the integral of u dv, you can split it up into uv minus the integral of v du. Okay, so in this problem we're going to make u equal to y, and we're going to choose the dv to be secant squared. Secant squared y. Okay, that means the du is equal to dy, and then that means that the dv is equal to secant squared, then the v, meaning the antiderivative, move backwards, is tangent y. Okay, so we can write that down over here. So equals, this integral equals uv, so y times tangent y, minus the integral from 0 to power of 4, and let me put that, it's being integrated from 0 to power of 4 there too. okay, minus the integral from 0 to pi over 4 of, let's see, it's v du. So that will be tangent y times dy. Okay, v du. Okay. Now the integral of tangent y is negative ln of secant y. Okay, so this becomes y times tangent y from 0 to power 4 minus ln of secant of pi over 4. Whoops, excuse me, getting ahead of myself. Secant of y integrated from 0 to pi over 4. Okay, and now we can plug in our limits real quick and see what we get for an answer for integral number 2. Okay, so we plug in a pi over 4 here. We get pi over 4 times tangent of pi over 4. And then minus, when we plug in a 0 here, well, 0 goes here. 0 times anything is 0, so it just stays 0. And then over here, minus, and let me put a parentheses here to make sure that everything inside gets this minus sign here. So we get ln of absolute value of secant of pi over 4 minus ln of secant of 0. Okay. So let's look at this one here first. Secant of 0 is equal to 1. Okay, so that's going to be the same thing as ln of 1. And as we know, ln of 1 is equal to 0. So that whole term goes away. And of course, this term is gone. So we have equals pi over 4 tangent pi over 4. And we will subtract ln of secant of pi over 4. Okay, so that's integral number 2. Here's integral number 1 up here. And remember, this was up here. This was what we were originally looking at. And we're going to plug our answers in. For integral 1, we're going to plug in a pi over 4 tangent pi over 4 right here. And then for integral number 2, we're going to plug in this pi over 4 tangent pi over 4 minus ln absolute value secant of pi over 4 in right here. Okay, so let me get another piece of paper. So let's just write it here. So we get W equals, and it's going to be the rho g pi out front, and then it will be pi over 4 tangent pi over 4, okay, minus the rho g pi of the other one, which is pi over 4 tangent of pi over 4 minus ln absolute value secant of pi over 4. And there's the end of that parentheses. Okay, now if we distribute this negative sign here to both of these and the rho g pi, distribute the negative sign, okay, you can see that when we distribute this one to this term and we distribute this one to this term, they're opposites. It's the same thing except they're opposite signs. Okay, so that's going to cancel out. Okay, this term with this term is going to cancel out, and then all we have to do is multiply this by that secant term. And remember, they're both negative, so W is equal to positive rho times G times pi times ln of absolute value of secant of pi over 4. Okay, now remember that, and let me go back and show you what we did there. This was the integral, the big integral that we did, and we plugged in our answers here, and we got this as an answer. Also remember that we were given that the rho is equal to 1,000 and the g is equal to 9.8, so W equals 1,000 times 9.8 times pi times ln absolute value of secant of pi over 4. Okay, and if you plug that into a calculator and approximate that answer, you will get 10,670.2.